All right, so I'm going to go ahead and get started. All right, so I'm going to begin today by talking about span. So this is something that we've talked about a couple of times in the past. I talked about it last time. I'm going to mention it again today. So first, let's just recall what the word span meant. So let's say we have a vector space, which I'll denote by a capital V. And then let's say we have some vectors, I'll call them V1, V2, and so forth up to Vk. So these are some vectors in the space V. Okay. All right, so the span of these vectors which you might denote by like span of V1 through Vk. Okay. All right, but the span of a collection of vectors, it's defined to be the set of all linear combinations of these vectors, so V1 through Vk. And something that I briefly mentioned last time is that given any collection of vectors, the span will always be a subspace of the given vector space. Okay. Now, if the span of V1 through Vk, so if the span is equal to the whole space, then we say that the vectors V1 through Vk will span the space V. And so equivalently, we can say that vectors V1 through Vk will span a space V if and only if every vector in V is a linear combination of the vectors V1 through Vk. All right, so if that's not too clear, all right, so again, just remember the span of a collection of vectors is the set of all linear combinations of them. So to say that the vectors span the entire space V should mean that every vector in V is a combination of them, all right? And then it's always useful to reformulate these definitions. So we can also rewrite this by saying that the equation C1 V1 plus C2 V2 and so forth up to CK Vk equals B. You can also say that this one has a solution for every vector b in the space V. Because remember, this is precisely what we mean by a linear combination of V1 through Vk. So saying that every vector V is a linear combination of them would be the same as saying that this equation will have a solution for every vector B. Okay. Okay, so then with that, let's just look at a example. All right, so let's take 3 vectors and we'll work in R3 for now. So that's vector V1, V2, let's make that -2, -3, 4. Then we'll take a third vector V3. So 5, -3, 5. So with these 3 vectors, let's ask if these 3 vectors span of R3. Yeah. So in order to answer this question, we'll check this condition here. So we want to take an arbitrary vector in R3. We want to try to express it as a linear combination of V1 through Vk. And then we're going to try to see if we're able to find a solution to this equation no matter what B is, okay? All right, so let's say here's our vector B. So I'm going to go ahead and set up this equation. So we're going to do C1 times V1 plus C2 times V2 and plus C3 times V3. We'll set it equal to the vector B. All right, now this gives us a system of equations. So I'll go ahead and write out the augmented matrix for it. So we have the first equation is 1C1 minus 2C2 plus 5C3 equal to B1. And so next we'll have -2, -3, -3, B2. And then finally we're going to have 3, 4, 5, and B3. All right. So now we want to begin doing some row operations, trying to see if there will be a solution to this. I'll go ahead and start downwards first. So I'm just going to do the standard elimination. So let's do row 2 plus 2 row 1. Let's also do row 3 minus 3 row 1. Okay. All right, so that will give us 1, 0, 0. And then let's see, row 2 plus 2 of row 1. So what is that going to be? -3, minus 4 is negative 7. Here, negative 3 plus 10, right? It's going to be 7. Here we're going to get B2 plus 2B1. And then looking at row 3, if we do row 3 minus 3 row 1, so we're going to get 4 plus 6. So I think that's going to be 10. What is this going to be? 5 minus 15 will be negative 10. And then B3 minus 3B1. All right, so it looks like that's what we'll get for our new matrix. So if we want to continue doing just a few more row operations, at least get it to the upper triangular form, I'll do a little bit of simplification first. Let me just take row 2 and let's just divide it by, well, let's do negative 1/7 times row 2. Likewise for row 3, if we maybe divide it by 10, I guess that will simplify things as well. So now we're going to get 0, 1, negative 1. And here I'll just write minus 1/7. And then times B2 plus 2B1. And then finally here, we're going to get 0, 1, minus 1. And then I'll just write out 1/10 times B3 minus 3B1. Now, if we do one more row operation to get it to upper triangular form, we do row 3 minus row 2. And that will leave us with 1 minus 2, 5, 0, 1, minus 1. And then you notice that we get a row of zeros right now. On the right, we'll still have B1 minus 1/7, B2 plus 2B1. All right, and then finally, doing row 3 minus row 2, we'll do 1/10, B3 minus 3B1. If we do minus row 2, we're going to have minus and negative, so it's going to become plus. And then 1/7 B2 plus 2B1. Okay, so I've now reduced it to the upper triangular form. So now looking at this equation, or looking at this matrix that we ended up with, does it look like there's always going to be a solution, no matter what the vector b was? Okay, yeah. So in particular, there will not be a solution if the right-hand side over here is non-zero. So maybe I'll write it like this. So there will be a solution only if this expression here is equal to 0. All right. Now let's remember what the original question was. So we were trying to check if these three vectors spanned all of R3. For them to span R3, we needed this equation to have a solution for every vector B. So we took an arbitrary vector B for the right-hand side. We tried to solve this equation, and we find that it does not always have a solution for every B. So because it doesn't always have a solution, that would mean that our vectors do not span R3, okay? All right, good. All right. So then let me make a few questions now from this example. So let's try to generalize. So in the example, I had 3 vectors in R3. But in general, let's suppose I have some number of vectors. I'll say v1 through vk. And let's say these were all vectors in Rn specifically for some n. Now, if we want to check if these vectors span Rn, okay, let's see how the last example worked. Okay, so it ultimately boiled down to having to solve this system of equations here. It's worth noting that the vectors v1, v2, v3 end up forming the columns of this matrix once we set up the system of equations. All right, so if I take these vectors and if I kind of do the same thing and put them into a matrix as columns, so v1 being the first column and so forth, vk being the last column, then we can say that these vectors will span Rn if and only if the equation ax equals b has a solution for every vector b. Okay. And if we continue looking at this example to try to gain some more insight, so here we ended up with no that did not span because there would not always be a solution for every b. And the reason why that's happening is in particular because we ended up getting this row of zeros here. So in order for there to have been a solution, no matter what B was, you could not have a row of zeros if there were to be a solution for every B. Right, so then equivalently for these vectors to span Rn, another way you can think of it is by saying that this matrix A will not have any rows of zeros. After you do elimination. And then one final way that you can rephrase all of this is to not have a row of zeros would mean that you'd have a pivot in every row. So if I want to think of it in terms of pivots, we can say that the vectors will span Rn if and only if this matrix A has a pivot in every row. Okay. All right, so for the moment, I'll just pause and ask if there are any questions about anything so far. All right, so to span Rn would mean that every vector, so to say that the vectors v1 through vk span Rn, all right, so that means that every vector in Rn, so maybe every vector b in Rn is a linear combination of these vectors v1 through vk. Right, so then this here would be relating to the definition of span. All right, but then all these other equivalent statements that I have here, these are equivalent statements that we sort of discovered, if you will, from working out our last example. Okay. All right, any other questions about anything so far? Okay, all right. So then next okay, so I'll make one more quick comment about all of this, and then I'll move on to something else. So in this situation where we have k vectors in Rn. So looking at this matrix A, all right, so first we notice that it has k columns. And since each vector has n components being in Rn, so that means there would be n components here in each column, meaning that there would be n rows altogether. So the size of matrix A is going to be n by k. So I think just something small that's good to note is that in order for there to be a pivot in every row, then we would need k to be greater than or equal to n. Because you can only have at most one pivot in each row and column. So k were smaller than n, then you could only have at most k pivots, so you wouldn't be able to have a pivot in all n of the rows. Okay. So that's just kind of something small that's maybe good to note. If you have k vectors in Rn, for them to span Rn, you do need k to be at least as large as n in order for them to possibly span, okay? That's kind of intuitive, so if I look at a very quick example, if I create any two vectors, and let's maybe quickly consider if the vectors v1 and v2 would span all of R3. Okay. So here we only have two vectors, but as we talked about, for R3, we would need at least three vectors in order to be able to span all of R3. So here we don't have enough vectors to span all of R3, so you could sort of immediately say no without actually trying to do any work. And this is kind of something that you've already done before earlier in this semester. Because what's the idea here is you only have two vectors, so like geometrically, we know that v1, v2 would span at most a plane in R3, but they wouldn't be able to span all of R3 because they wouldn't be able to fill up all like 3 dimensions. They'd only fill up a two-dimensional plane inside of R3, okay? All right. Yeah, so this is something that we kind of understood from a geometric perspective before. But then here, this was sort of maybe like an algebraic explanation for why we would need at least three vectors in R3 in order to span, okay? All right, so now I wanted to talk next about the column space. Okay, so if I have a matrix, it can be any size matrix. So I'll just give it a generic size m by n. The column space of A which in this class we denote just by C of A. Right, the column space of A is defined to be the span of the columns of the matrix A. Now, again, remember that span of a collection of vectors was the set of all linear combinations of them. So you can rewrite this by saying that the column space of A is the set of all linear combinations of the columns of A. And then let's recall that if A is a matrix, and let's label the columns as A1 through AN. And then let's say if it had this vector x with components x1 through xn. Okay. So you guys will remember how when we multiply A with x, that forms a linear combination of the columns of A. So then another way that you can think of the column space of A would be to say that it's the set of all vectors B for which the equation AX equals B has a solution. Because if B is equal to AX, then that would just mean that B was a linear combination of the columns of A. Okay? And I guess it's not a big deal, but let me see here. If A is size m by n, then x would have to be a vector size n by 1 in order to multiply A and x. And the vector B would be size m by 1. So we said B is a vector in Rm. Okay. Okay, now, so here again, we've defined the column space of A. We've written out a couple different ways that you can think of the column space. Okay. So each of these perspectives are useful at times. So it's good to keep them all in mind. I would like to return real quickly to the example that we did earlier over here. Okay. All right, so if we take this matrix A over here, and we ask what would the column space of A have been in this example? Okay. All right, so first, by definition, the column space of A is just the span of its columns. So in this case, would just be the span of the vectors v1, v2, v3. And then we also mentioned how the column space of A can be thought of as the set of all vectors B for which the equation AX equals B has a solution. So if we look at this perspective, and go back to that example. So we set up the equation AX equals B, and after the elimination, we see that for there to be a solution, the B has to satisfy this equation here. So then we can also say in this example that the column space of A would be the set of all vectors B satisfying this equation. Okay. Because it's precisely for this set of vectors B for which the equation AX equals B would have a solution. Okay. So then here we have kind of two different but equivalent descriptions of the column space of this matrix A. All right, so then let's see here. I'll make a comment that in your homework assignment, so there's one of the questions, I don't remember which one. I think it was the very first equation, or sorry, the very first question in your homework assignment, where it gives you some vectors, and one of the questions was worded something like, find a linear relation that the vector B must satisfy to be in the column space of A. So if you look at, I think it was the first question, you'll see one of the parts with the question worded something like that. So they'd be referring to this type of equation here. So this is a linear relation that the vector B needs to satisfy. To be in the column space of our matrix A over here. So if you want to find this linear relation, you can see what the procedure for that would be, which is just to set up this augmented matrix, do the elimination. And if you get a row of zeros, you're going to need the right-hand side equal 0 for there to be a solution, okay? All right, so then I'll just pause again, and I'll ask if there were any questions. All right, so then in that case, I will continue. So that was just talking a little bit about the column space. So then next, I'm going to talk about linear independence a little bit. And this is something that we've already talked about before, but now we're going to revisit it. So first, let's recall what the definition is. So we have a vector space V, and again, we have some vectors in this space. All right, and so the definition was vectors are linearly independent if, I'll write it as if the only solution to the equation C1V1 plus C2B2 all the way to CKBK. So if the only solution to this equation where it's set equal to 0 is what some people call the trivial solution, where all of the coefficients are equal to 0. Okay? All right, now over here, this expression on the left-hand side is a linear combination of the vectors v1 through vk. So another way you can think of linear independence is saying that the only linear combination of these vectors that will equal the 0 vector is the one where you just multiply all the vectors by 0. Okay? All right, but let's just set up a example real quickly. Let's actually use the same vectors that we had before in the first example. So we had these vectors v1, v2, and v3. And let's ask the same question, or rather, let's ask now if these two vectors are linearly independent. Okay. Okay, so to check if they're independent, we want to set up this equation. So C1 V1 plus C2 V2 plus C3 V3 equal to 0. Okay, so we set up this equation, and now we want to check what are the solutions to this equation. So certainly, one solution will be if C1, C2, and C3 were all 0. That would definitely give us 0, 0, 0. If that's the only solution, then these vectors would be independent. Otherwise, they would not be independent. Okay. So then, again, this gives us a system of equations, which we can solve by setting up the augmented matrix. So right now, I think it's worth noting that for linear independence, it's a little bit similar to checking if they span or not. But the difference, at least right now, is that for span, we remembered that we had just B1, B2, B3 on the right-hand side, but for independence, we have 0 on the right-hand side instead. Okay? All right. And if we go through the process of elimination, all right, so we did it earlier, so let me just write down the end result that we got, okay? So this is just from earlier where we already did elimination, and we saw that we could reduce the matrix A to this matrix here. Okay, so now looking at everything in this reduced matrix, can we say that there was a unique solution to the system of equations, or does it look like instead that we're going to have infinitely many solutions? Okay, so in this case, we end up having infinitely many solutions, all right? And we've talked about it before, so why is it that we have infinitely many solutions to the system of equations? All right, so let's talk about why that would be the case. Oh, actually, just before that, real quickly. So if we notice right now that there are infinitely many solutions, we can actually just answer the question right now, are they independent? So the answer would be no. Because by the definition, to be independent, the only solution has to be that C1, C2, C3 are all equal to 0. But here we're saying that's not the only solution because we have infinitely many solutions instead. Now let's recall why is it that we have infinitely many solutions right now. If I were to write out the corresponding system of equations, so here we have the equation like 1c1 minus 2c2 plus 5c3 equal to 0. Then we also have c2 minus c3 equal to 0. So because we have only two equations in the end, we're only going to be able to solve for two of these variables. And then that means we're going to have one variable, which is free, okay? In this case, we're going to choose the variable C3 to be free. And as a reminder on which variables we typically choose to be free. So this is something we talked about some time ago. But going back to the reduced matrix, any column that is missing a pivot will give you a free variable. So in this case, only columns 1 and 2 have pivots, and column 3 is missing a pivot. So because column 3 is missing a pivot, we can choose the third variable, C3, to be free. And what we did with free variables was we assigned to them a parameter, which is just another variable. And I would typically use t for the parameter. And then looking at this system of equations, we have C2 is equal to C3, meaning C2 is equal to t. And in C1, if we plug in t for C2 and C3, you should get C1 would be negative 3t. So here the idea is we solve for C1 and C2 in terms of the free variable c. And what we mean by saying that C3 is a free variable means that it's free to take on any value, meaning that t can be any real number. And because t can be any real number, that's why we're getting infinitely many solutions. Okay? Now, it is important that you guys know how to go through this process of identifying when you have infinitely many solutions, and then being able to write out your infinitely many solutions in this kind of form. So we're definitely going to do another example later on, but what I want to emphasize right now is for there to be infinitely many solutions, there has to be a column without a pivot, because that is what will lead to having a free variable, which then leads to infinitely many solutions. All right, and so then, just as I did with span, I want to use the last example to make some observations regarding linear independence. So if I have k vectors in Rn, and again, if I put them into a matrix A as the columns, so for these vectors to be independent, okay. So just first from the definition, for them to be independent, it means that the only solution to this system of equations is that C1, C2, C3 have to equal 0. Or just rewriting that slightly, we can say that they're independent if and only if the equation AX equals 0 has only one solution. All right, but then we talked about how you'll have infinitely many solutions whenever you have a column that's missing a pivot. So to have a unique solution, that would mean that every column has to have a pivot instead. So in terms of pivots, you can say every column has a pivot. Maybe just to emphasize a non-zero pivot, although I don't think you consider zeros to ever be pivots, so I don't think I really need to stress that. But just in case, I'll emphasize it. And so if you compare this to span, so the last observation that I made about span is for the vectors to span Rn, you needed every row to have a pivot. So for linear independence, you see it's kind of flipped a little bit, where to be independent, you need every column to have a pivot instead, okay? And then I'll just make a small kind of interesting note, which is that in order for there to be a column in every pivot, if we think about the size of the matrix A, we would need K to be less than or equal to N. in order for this to work. Because if you had more columns than rows, then it wouldn't be possible to have a column in every pivot. So like the columns over here would not have pivots, for instance. Okay. So there has to be fewer columns than there are rows in order to ensure that you could have a pivot in every column. Okay. All right, so I'll pause for the moment and I'll ask if there are any questions. And then if not, I'll set up one final example and I'll talk a little bit more about some stuff. So I'm going to talk about, real quickly, I'm going to introduce the null space of a matrix. Okay, so let's say we have any matrix, doesn't matter what size it is. So the null space of A, which we denote by N of A, is defined to be the set of all solutions to the equation AX equals 0. So going back to the observations that I had here about linear independence, I can actually put down one more observation using the null space. Okay, so here, to be independent, the only solution to this equation AX equals 0 has to be the solution X equals 0. And since the null space is the set of all solutions to this equation, another way to phrase it is by saying that the null space of A will consist of nothing but the 0 vector. Which some people will phrase this by saying that the null space of A is trivial. Okay. So that's another sort of equivalent statement for linear independence. All right, and so then finally, I want to do one more example, talking about the reduced row echelon form of a matrix. All right, so first, what is the reduced row echelon form? All right, so first I'll list what the properties of the reduced row echelon form are. So first, all the pivots have to be equal to 1. Second is that pivots must be ordered in the usual way. So meaning that each pivot appears below and further to the right of the previous one. So third, all entries above and below each pivot must equal 0. And then finally, any and all rows of zeros must be at the bottom. All right. So if you have a matrix A and you want to put it into reducible echelon form, so it's just going to involve kind of doing row operations in the usual way. But for a reducible echelon form, you'll need to do a few extra row operations. So normally we only get zeros below the pivots, but for the reducible echelon form, we also want to get zeros above all of the pivots. And then we also want to make sure all the pivots are equal to 1. So if you get a pivot that's not equal to 1, you would need to divide that row by the pivot in order to make the pivot equal to 1, okay? And a few things about RREF real quickly is that the reducible echelon form of a matrix is unique. So as you do your row operations on A to reduce it to the reducible echelon form, it doesn't matter so much how you do your row operations, but once you get it into the RREF, you'll always have the same RREF no matter how you did your row operations. And we won't talk too much about it this week, but the reason why the RREF is important is because certain information about the matrix A is going to be most transparent when you look at the reducible echelon form. So I'm going to set up one example of reducing a matrix into the reducible echelon form. And I'm also going to highlight some of the information that we can glean about the matrix A from the reducible echelon form. So I'll try to make this somewhat quick. So here is our matrix, and what I'm going to do right now is just reduce it into the reducible echelon form. So I'll try and do this rather quickly. So I'm going to start with the usual row 2 minus 2 row 1 and row 4 plus row 1 to make these equal to 0. Whoops. And just quickly computing the rest of row 2. 7 minus 6 is 1. Negative 3 plus 4 is 1. 2 minus 2 will be 0. And negative 7 plus 6 is negative 1, okay? If I do row 4 plus row 1, it'll be negative 2 here, negative 2, 1, and then -3, okay? Okay, let's see here. All right, so then next, we have our next pivot over here. So for the reducible echelon form, we want to get zeros above and below it. So fortunately here, we already have a 0 on top. But if I didn't have a 0, then I would need to perform a row operation to eliminate whatever was above it, okay? But in this case, I just need to do row 3 minus 3 row 2. And row 4 plus 2 row 2 to eliminate these two entries. Okay, and then let me see here. If I do row 3 minus 3 row 2, -1, and row 4 plus 2 row 2. I think that's a row 4 plus 2 row 2. Okay, so I think I get -5 there. All right, and so then next, I'm going to do, so here's my next pivot. So right now I'm just circling my pivots. And I need to get zeros beneath it, but also above it. So this time I'm going to have to do row 1 minus row 3 to eliminate this 1. And then we'll do row 4 minus row 3 as well. And then real quickly, row 1 minus row 3. And row 4 minus row 3, -4. So we have pivots here, here, here. And we've got this one final pivot, so I'm going to have to multiply row 4 by -1/4 first. Because for the reducible echelon form, every pivot must be equal to 1. And then finally, if we just now do, let's see here, row 1 plus 2 row 4. So using the pivot to eliminate the -2. As well as row 2 plus row 4 and row 3 plus row 4. That will finally give us the reducible echelon form of the matrix A. And so hopefully I didn't make any mistakes when I did that. So I was rushing a little bit. So here are the 4 pivots. So again, all the pivots have to equal 1. They have to be ordered so that the next one is further down and to the right. Zeros below and above all of the pivots. And we didn't have any rows of zeros, but if there were any rows of zeros, we have to make sure that they're at the very bottom. So that might entail swapping some rows as to get any rows of zeros to the bottom, okay? Okay, so I wanted you to do just 2 more things, and then I will end my review. All right, so first, let's suppose that I wanted to find the null space of this matrix. So remember that the null space was the set of solutions. I see, but wait, let me see. Yeah, okay. So it's the set of solutions to the equation ax equals 0. So here I've already reduced my matrix. So if I now want to solve this equation to find the solutions and get the null space, I would do as I did before, write out the corresponding system of equations that we have. So first we have in the first row, 1x1 plus 0x2 plus 3x3 minus 2x4. And we're going to set it equal to 0 for the null space. So remember, null space always has 0 on the right-hand side. Next, we're going to have 1x2 plus 1x3 plus 1x4. Again, equal to 0 on the right for the null space. Then we're going to have x3, x4. So here we have just 1x5 equals 0. And then here it's just going to be 1x6 equal to 0. Okay, so we have these 4 equations. So we're going to only be able to solve for 4 of the unknowns. We're 2 free variables because there were 2 columns without pivots. So we'll call these the free columns. Okay. All right, but because these columns don't have pivots, that means that the 3rd and 4th variables, we'll choose these 2 variables to be free. Okay, so then x3 and x4 can take on any value. So therefore, we're going to assign to them a parameter. Then we'll write out the remaining variables. So we see that x5 and x6 must be equal to 0 from these 2. Looking at this equation, x2 must equal minus s minus t. So moving these over. And then finally, in the first equation, x1 is going to be minus 3s plus 2t. So then this would be the set of all the solutions to our equation ax equals 0. So now I'm just going to rewrite that. So remember that the solutions give us the null space. So then we can say that the null space is the set of all vectors x. For which x1 is going to equal negative 3s plus 2t. X2 is going to be negative 1s minus 1t. X3 is going to be 1s plus 0t. x4 is 0 S's and 1 T, and then x5 and x6 are 0 S's and 0 T's. So here I'm just writing it out in a particular way. All right. So then this that we've written out here, this would be the general solution to the equation ax equals 0, which by definition, the solution to this equation gives us the null space. So here, the way that I wrote it out is somewhat revealing. So if I call this, let's take this vector and this vector. If I just call them a u and v real quickly. Here we're saying that the null space consists of all linear combinations of the vectors u and v. So then geometrically, this is in 6 dimensions, so it's kind of hard to draw, but you've got 2 vectors, u and v. And so if you take all possible linear combinations of them, that should end up forming a plane. So we can kind of see geometrically that in this example, the null space of A is going to be a plane in R6. Specifically, it's a plane spanned by these 2 vectors, u and v. Okay? All right. And then I want to make one final observation. So I'm going to go back to the reducible echelon form of A. All right. So finally, looking at the matrix A originally, and looking at its reducible echelon form, if you look at the reducible echelon form, it gives us some information about these, the free columns of the matrix A. So in particular, it reveals to us that the free columns are actually linear combinations of the pivot columns of A. And here I'm just going to have to quickly show you how it works. So looking at the third column, which was one of the free columns, we have the numbers 3, 1, 0, 0. So that's going to tell us that the third column in the matrix A is equal to 3 times the first pivot column plus 1 times the second pivot column. And then I guess a plus 0 times the third pivot column, and plus 0 times the fourth pivot column. So I won't, well, I'll write it out, but yeah, so we'll just real quickly, I'll write this one out. Okay. And here, if you look at the original matrix to try to confirm this, so the third column of the original matrix A was 3, 7, 3, negative 5. And the first pivot column would be the first column. The second pivot column ended up being the second column because that's where the second pivot was. So you can kind of confirm right now, if you do 3 times this vector plus 1 times this vector, that it does end up giving us this vector here, okay? So it may not have been clear that the third column of A was 3 times the first column plus 1 of the second. But once we get it into the reducible echelon form, the entries that we see here reveal that information to us. And then finally, just looking at the fourth column, which is also a free column. Based off the numbers that we have in the RREF, it should be -2 times the first pivot column, and then +1 times the second pivot column, and then +0 times the third pivot column, +0 times the fourth pivot column. And then just looking at the original matrix, the fourth column was -2, -3, 3, 0. If you do -2 times the first column of A, +1 times the second column of A, we should find that this combination does indeed produce the fourth column within A, okay? All right, and I'm over time, so I'm just going to end my review at this point.